Hello students, welcome to class 11. Today we will discuss about units and measurement. In this chapter, we will discuss about system of units. System of units. Till 10th standard, in physics you have studied about various physical phenomena. In that you have studied about the name of physical quantity, you have studied the unit of physical quantity, you have discussed the definition of that physical quantity, you have also wrote the unit of that as well as formula also. Different physical quantities you can represent into their units into different system of units. In olden days there was a system called FPS system. FPS, that system was measuring three physical quantities: length, mass and time. Length, mass and time. In this system, FPS, length was measured in terms of feet, mass was measured in pound and time in second. Then another system came that is called as CGS system. In CGS system, length is measured in centimeter, mass in gram, and time in second. Another is MK system. In MK system, length is measured in meter, mass in kilogram, and time in second. Apart from this, there is one more system called as SI system. SI stands for System International. SI units, it means System International Units. In this system, there are 7 physical quantities which are measured. And these 7 physical quantities, they are called as fundamental physical quantities. So these 7 fundamental physical quantities are these 3, that is length, mass and time. Apart from that, one more is electric current. Another is light intensity. Another is thermodynamic temperature, and one more is amount of substance. So these are the 7 physical quantities which are measured in this SI system. This system that consists fundamental quantities, supplementary physical quantities, as well as derived physical quantities. Fundamental physical quantities, there are 7 quantities called as fundamental physical quantities because any other physical quantity that can be obtained by either multiplying or dividing these quantities. And that's why these quantities, they are called as fundamental physical quantities, and these quantities are having dimension. These quantities are having dimension. So length, mass, time, electric current, temperature, light intensity and amount of substance. These are the 7 fundamental physical quantities. The dimension for this length, it is capital L, mass it is M, time it is capital T, electric current it is ampere, temperature it is Kelvin, K, light intensity candela, amount of substance mole. So these are the dimensions for these fundamental quantities. Another category that is called as supplementary physical quantities. The difference, basic difference between fundamental and supplementary quantities are that fundamental quantities are having dimension, whereas these quantities are dimensionless. Why it is dimensionless? Because they are the ratio of same physical quantities. For example, plane angle. Angle, as it is defined as the arc upon radius. Arc, that is measured in meter. Radius, that is also measured in meter. It is the ratio of length divided by length. Similarly, other physical quantities also, they are the ratio of same physical quantities, and that's why they have a unit but they have no dimension. So that is the basic difference between fundamental and supplementary physical quantities. And third category, that is called as derived physical quantities. Derived physical quantities, they are the physical quantities obtained by multiplying or dividing these fundamental quantities. Example, suppose speed, that is defined as the rate of distance traveled. This distance traveled upon time taken. Distance is measured in unit is length, meter, and time is second. So it is meter per second, or that is the length upon time. Okay. Similarly, acceleration, that is the rate of change of velocity. That is and velocity, as it is defined as the displacement upon time. So again it is length by time, again divided by time. So what ultimately we can say that all these physical quantities, they are derived using these fundamental quantities. Okay. Like momentum, it is a product of mass and velocity. So here there is a product of two physical quantities. Okay. So that way various physical quantities can be obtained by multiplying and dividing various fundamental quantities, and that's why all other physical quantities which you study, they are coming into this category called as derived physical quantity. So SI system, that consists basically three category of system, these quantities: fundamental, supplementary, and derived. So in SI units, fundamental physical quantities: length, mass, time, electric current, light intensity, temperature, and amount of substance. Fundamental units for this physical quantity are: for length it is meter, for mass it is kilogram, for time it is second, electric current it is ampere, light intensity candela, temperature it is Kelvin, amount of substance it is mole. For these fundamental units, there are symbols also. Mass, it is having this meter, it is having symbol M, kilogram it is kg, second it is S, ampere represented by symbol A, candela CD, Kelvin it is K, mole it is mol. So these are the symbols for this fundamental physical quantities. Till 10th standard, for any physical quantity, you are writing its definition, you are writing its formula, you are writing its unit in any of the system of unit. This year onwards, one more thing which is added, that is called as dimensional formula. Here for all these physical quantities, there is one more way to represent, that is with its dimensional symbol. So for length, dimensional symbol, that is represented by symbol capital L, mass it is represented by symbol M, temperature it is represented by symbol T, electric current that is represented by symbol A, light intensity it is CD, temperature it is Kelvin, that is K, and amount of substance it is mol, mole. So these are the symbols for these fundamental physical quantities. These are called as dimensional symbols. Now what is new, that is, as you are writing the formula, from the formula you are writing the unit in any of the system of units. Similarly, now you will be able to write the dimensional formula. Let us have an example. One simple example, if we take, for example, suppose if we take the example of force, you know that force, it is defined as a push or pull. Okay, that is the definition. For force, the formula you write, that is force F is equal to m into a. M is mass, a is acceleration. If you want to write the unit of this physical quantity in terms of fundamental units, you can write the SI unit is For mass it is kilogram, acceleration it is meter per second square. So this is the unit in fundamental physical quantities. There are some special names also for this kind of physical quantities, and that is for this force. SI, unit of force, also represented by symbol N, called as Newton. That is from the name of scientist who stated the laws of motion. Now, if we are able to write this unit, then we can also write the dimensional symbol also. The dimensional formula for any physical quantity is represented in terms of power m, l and t in a bigger bracket. For example, for here m, l and t, power if we write kilogram, that is for, that symbol is m. So how many times kilogram it is? 1 time, so you can write m1. M, that is stands for meter, that is for the dimension is L, so 1 time is L1. S, that is for second, it is for time, symbol is T, power is -2. So here directly from this unit you can write the dimensional formula. Now generally when the power is 1, it is not necessary to write, so you can also write this as mLT -2. So this way you can represent the physical quantity with its dimensional formula. So for any physical quantity you can write the definition, you can write the formula, you can write the unit in SI system or any other system, as well as you can write one more thing, that is dimensional formula. Now the question is that what is the use of writing this dimensional formula? What is the importance of this? To convert unit of any physical quantity from one system to another. The relation you can write for that is N1, M1 raised to A, L1 raised to B, T1 raised to C is equal to N2, M2 raised to A, L2 raised to B, T2 raised to C. Here M, L and T are having power A, B and C. M1, L1, T1, that are the dimensions in system 1. M2, L2 and T2 are the dimension in system 2. N1 and N2 are the multiplying factors. They are the constant values. Example, let us take convert unit of force from SI system to CGS system. SI unit of force in CGS system is dyne, whereas in SI system it is Newton. In SI system it is Newton, and 1 Newton is 1 kilogram meter per second square. In CGS system it is dyne, and 1 dyne is 1 gram centimeter per second square. Dimensionally if you write kilogram, that is mass having power 1, meter length having power 1, second having power -2. Similarly here also. Now 1 Newton is 1 kilogram, 1 meter second is to -2. 1 kilogram, that is 1000 gram. 1 meter is 100 centimeter. Second is equal to second. So 1 Newton you can write as 1 kilogram meter per second square, that is 1 kilogram is 1000 gram, 1 meter is 100 centimeter, second is second. So dimensionally if you write in this second case it is M2, that is 1000 times M2's power 1, L2 it is 100 times L2 power 1, T2 that is 6. So M1 power 1, that is here 1000 times M2 power 1. L1 times 1 power 1, that is 100 times L2 power 1. T1 power -2 is equal to T2 power -2. So total is 10 is to 3, M2 10 is to 2, that is 10 is to 5 times M2, L2, T2 is to -2. So value of multiplying factor N2 which you get, that is 10 is to 5 when N1 was equal to 1. So here the relation you get, that is 1 Newton is equal to 10 raised to 5 dyne. So this way you can convert a unit from one system of unit to another system of unit. Another application is to check the dimensional correctness of any relation. We are using various physical quantities, the relation among them, whether these relations are dimensionally correct or not. To check it, you can use the concept of this dimensional analysis. Example, let us take example of say work. work is force into displacement. W is equal to F into S. Work, it is a scalar quantity, but force and displacement are vector quantities, so can be represented in this way. We will study this later on. Now here LHS, it is work, W, and the dimensional formula of work is M1 L1 M1 L2 T minus 2. Right side it is product of force and displacement. Dimensional formula of force is M1 L1 T minus 2. Displacement M0 L1 T0. So here it is M1 into M0 power is 1 plus 0, that is 1. L1 into L1, that is 1 plus 1, it is 2. Minus 2 plus 0 is minus 2. You can see LHS and RHS. Dimensionally LHS is equal to RHS. So the relation is dimensionally correct. This way you can check the dimensional correctness of any relation between physical quantities. Third is to derive the relation between various physical quantities. This is very important application. You can derive the relation among various physical quantities. Let us take an example. Suppose if you take a stone, tie it with a thread, and if you revolve it in a circular path, okay. In this event, the various physical quantities which are in the role are: one is the radius of circular path, mass of the object, and its speed. Now, when we do this event, how long the object is executing circular motion till the string is in your hand. It means that keeping the string in your hand, what you are doing, that is certain force you are providing to this string that is acting toward the center. That is called as centripetal force. That is called as centripetal force. Now the centripetal force, that may depend on which factors. So factors which are involved, the physical quantities which are involved in this phenomenon, we can say that it may depend on mass of the object, it may depend on the radius of circular path, it may depend on the speed of object. Now how it depends, we don't know. Maybe it is a direct relation, indirect relation, linear relation, non-linear relation, whatever it can be. Let it is having power, say A, B and C. We don't know what is the value of this A, B and C. Okay. So we can derive this relation, we can find the value of A, B and C using the concept of dimensional analysis. What to do for that is, here we can say that AB is, it may depend on all these factors. So combining all this, M raised to A, R raised to B, V raised to C, let the proportionality constant, if it is K, we can write the relation as K, M raised to A, R raised to B, V raised to C. Now what to do that is, on both sides you can put the dimensional formula of these physical quantities. LHS, it is force dimensional formula is M1 L1 T minus 2. RHS K is the proportionality constant and it has no dimension. M is the mass, so dimensional formula M1 L0 T0 power A. R is the length, distance of power M0 L1 T0 power B. And V, velocity, it is M0 L1 T minus 1 power C. These are the dimensional formula of M, R and V. Now, if we simplify this, it is M raised to 1 power either M raised to A, L0, T0. Here M raised to 0 raised to B, that is 0, L raised to B, T raised to 0. M raised to 0, L raised to C, T raised to minus. Again, if you multiply these quantities with the same base, that is M raised to A plus 0, M raised to A, L is 0, B and C, that is B plus C, T is 0, 0 and minus C, so that is T raised to minus. Now both sides, if you compare the power of m, l and t, you're comparing this power, you can say a is equal to m raised to a is m raised to 1, a is equal to 1, m raised to b plus c is equal to 1, so b plus c is equal to 1, and minus c is equal to minus 2, minus c is equal to minus 2, so you get the value of c is equal to 2, a is equal to 1, so from this you can get that for b is equal to 1 minus c, that is equal to 1 minus 2 is equal to minus 1. This way you are getting the value of a, b and c. Putting these values in this relation, you will get f is proportional to m raised to a is equal to 1, r raised to b is equal to minus 1, and v raised to c is equal to 2. So you get the relation f proportional to mv square by r, f is equal to k mv square by r. Okay. So this is the relation you derive between physical quantities. This is the use of dimensional formula. So this way, for different physical quantities, you can derive the relation between. Apart from applications, there are some limitations also. See here, as we are comparing the power of m, l and t, maximum we can derive the relation among 3 physical quantities. So if there is a relation between more than 3 physical quantities, then it is difficult to derive the relation. Another one thing, when we derive the relation, we get the single term. So any relation having single term, that can be derived. But if you want to derive the relation, suppose a displacement as ut plus half at square, okay, then directly you cannot obtain this relation. You have to derive the relation, that is as ut as is proportional to at square. So individually you can derive these 2 relations, and then you can get the combined relation. So that way at a time you can get only single term relation. Another one, value of a proportionality constant is not obtained. So here half, it is a proportionality constant. You cannot get this value using dimensional analysis. That is obtained by experimental verifications. Another relation containing dimensional constants. For example, suppose gravitational force F is equal to gm1 m2 upon r square. Capital G, here it is a dimensional constant, it is a dimension. But this kind of relations are not obtained using dimensional analysis. Another relation containing trigonometric functions, logarithmic functions, exponential functions, these are dimensionless. So we cannot get this kind of relations also using dimensional analysis. So these are the various limitations of this dimensional analysis.